Hi class, we are now on 19.7. This is entropy changes in chemical reactions. So we're actually going to be calculating. So the first thing we need to do is understand standard state, and you should be familiar by now with this little dot that comes up. That means that there are standard conditions when trying to calculate a change. And in this case, for a gas, a pure gas is exactly at 1 atm, atmosphere. For a liquid or solid, it is a pure substance in its most stable form at exactly 1 atm pressure and a temperature of interest, which is usually 25 degrees Celsius. A solution is at a concentration of 1 molarity. So these are the standard state conditions, so this is more of a review. Now we're going to take a look at the third law. So the third law has to do with absolute entropy, and it states that a substance that is states a substance that is perfectly crystalline. So remember, crystalline. This is a lattice structure that is very ordered, patterned out. Is a perfectly crystalline at 0 Kelvin, has an entropy of 0. A perfectly crystalline substance at 0 should have perfect order. So completely patterned, completely aligned, layered, structured, everything is just ordered. But keep in mind that when the temperature raises, that substance increases in entropy. So as it absorbs heat, the energy disperses it. So we're only talking about at absolute temperature, which is 0, that this happens. But when the temperature raises, it will go through those entropy and disperse that energy. A crystal, not being perfect, will contain some entropy. So when we're discussing 0, meaning absolute entropy at 0 joules per mole per Kelvin, this is completely perfect. Nothing else going on with it. Okay, so now let's take a look at using standard molar entropy. So we're going to look at this, and the units are joules over mole per Kelvin. Thermodynamic conditions are 298 Kelvin, 1 atm, which I've already discussed, in 1 molar solute concentrations. How do we determine the changes? Remember, because it's a state condition, we only worry about the final versus initials. So in this case, it would be products minus reactants. M and N are the coefficients and the amount of those. This should look very familiar because we've done this, or you have done this, doing standard enthalpy of formation. So this isn't any different, but there are different values for these. So what are the different values? Well, although the standard enthalpy of formation, delta H, of an element is 0 kilojoules per mole, the absolute entropy at 25 S is always positive. So we're not dealing with 0 values when we're dealing with entropy. And I'll point that out on the next page. Where if we were looking at the enthalpy of formation, this would be 0. But however, it isn't for a gas here. This has actually got a value to it. So you need to be able to determine the distinct difference between the enthalpy values and the entropy values. Make sure you remember that they do have values to them. All right, so let's do some problems. Predict the sign of the change in entropy and calculate the standard entropy change associated with the reaction of gaseous hydrogen and gaseous oxygen to form water vapor. So you may have seen some of this before, but we're going to expand on it. So first thing, write a balanced equation. The prediction. So now we want to predict make sure we're kind of understanding the problem before we even work the problem. The number of moles are decreasing. We have 3 on the reactant side and 2 on the product side. So this prediction means that we believe that this is going to decrease. So the entropy will be negative. All right, so now we're going to rewrite the equation so that we can calculate the change. And as you can see, we have products minus reactants, and the coefficients play a part in it. So we set it up with, you can see the water as a gas as our products, and then we have as our reactants, we have hydrogen gas and oxygen gas. And now simply pulling up, and there's a chart in the beginning that you could pull this information out of it, and we plug in those values and just do the math on it. The change in entropy is negative 89.0 joules per Kelvin. This matches what we expected. There should be a decrease in entropy because of the moles going down, and that negative indicates that. Okay, so predict the sign of change of entropy and calculate the change in entropy when 72.85 grams of liquid mercury is vaporized. Again, you may have seen this one. So start by writing a chemical equation for the process. Sometimes I find problems and I change them up a little bit to match what the subject matter is. So what do we predict here? We predict that this is going from a phase change from liquid to gas. So we expect the entropy to increase, and that should be positive. So from here, same as the other one, we set it up. Products minus reactants. Make sure you are familiar that the coefficients go in here. Now we substitute that for the actual reactants and products. Plug in the numbers by looking at the table, and we can start plugging this in. So the first thing we do is we take the delta A, the entropy. We can see that we plugged it in and we have a value of 99.1 joules per mole per Kelvin. However, we're given an actual mass here, but now we have the value for the entropy. So we can now get our answer. So we take 72.85 grams, we use the molar mass, that gets us to moles. Now we can use this value, the moles will cancel out, the grams canceled out, and it will give us our value of joules per Kelvin. And this is a positive number, so which is what we expect. So this will actually increase in entropy, and it does. Standard molar entropy, a review, is an S with that nice little dot as a superscript. It is an extensive property, meaning that it does matter how much is there that we're calculating. Standard molar entropy values are for 1 mole of a substance. So when you look at a table, that is always for 1 mole. And things that affect it are the particular state, because you can see if you look at a table here, the different values for liquids and solids and gases. I probably did that too fast, but you understand. A particular allotrope, a particular molecular complexity, a particular molar mass, and particular degree of dissolution. We're going to break these down. So here again is another chart. Remember, I combined slides from another book, and I think sometimes those are better. So this is from this one, so you can see. Remember, the units are joules per mole over mole per Kelvin. So the relative standard entropy. So the states, depending on what state you have, that's also going to give you a value that's either larger or smaller. So if we take a look here, we have water that's at a liquid, which is 70 joules per mole per Kelvin, but a gas is at 188.8. So you can see it has a larger entropy value because gas has more energy states that the energy can be dispersed into, and it's more disordered. So this makes sense. So the liquid state has a large entropy than the solid, but gas has a larger entropy than both. Relative standard entropy is a molar mass. So here we take a look at these molar masses, and we notice that xenon, which is the largest, has a larger value than the rest of them when it comes to standard entropies. That is because the bigger, the heavier the atoms, they are more close together. They are not as spaced apart. And because they are so close together, they're more closely spaced. So the energy states are have a greater dispersal of the energy at a given temperature. So they have, let me see, I'm not explaining this right. They have greater entropy because they're closer together, which allows a greater dispersal of energy compared to the smaller ones that are more spaced apart. That makes sense. So molar mass, the larger they are, they have more, allowing more dispersal states of energy. Got it. Allotropes. Allotropes are some elements exist in 2 or more forms. Carbon has diamond and it has graphite. And what's different between them is the arrangement of atoms is different, and you can see the molar entropy values are also different. And that is because the way that they arrange, one will be less constrained than the other one. And if it's less constrained, excuse me, it will have a larger entropy. So think of a solid. A solid can't really do much compared to a liquid. And it's the same as this. When it's a solid, then the pattern of the atoms allows some more movement. And if it allows more movement, then it's going to have more energy states to allow entropy to be dispersed. And then molecular complexity. So with molecular complexity, what this means is that the more complex it is, the more entropy states are allowed to have dispersal of that energy. So if you look at argon, argon is by itself, but you see we have NO. NO is a molecule, which means that there's more than just one, and the molecules have greater entropy than free atoms. They have So as more complex over simple will have a greater value of entropy. And more energy states are also available. So if you over a free atom, this one, it makes sense. It's going to have a larger value. And between this more is more complex than this one, so it's going to have a larger value. And then this covers here. So this is showing you an idea of the energy states or the motion that gases NO can have. So when we look at argon, it's a free atom, but it only is allowed to have one form of energy, and that is a translational motion. So if we look, that's the first one right there. These bonds kind of vibrate back and forth. However, with NO, it can take on different forms of energy. In this case, it can take translational, rotational, which means that these spin, and then it can also take vibrational. So there's a bunch of different energy states going on for the molecule of NO over what argon has, and argon only has this one. So because it has more energy states, it has a greater disposal of entropy, the energy. Now, we look at dissolved solids. They have a larger entropy because once they're dissolved into a solution, they have allowed those molecules to disperse. That means greater entropy compared to what a solid is, because a solid, again, if you even think about these, has only certain vibrations, where when you have something that's in ionic form, it can spread out more than what is in the solid form. Okay, so now with that, let's arrange these gases in order of increasing standard molar entropy. So the easiest thing to understand here is we can look back at argon and NO. Molecular complexity. Are we dealing with a free atom or are we dealing with a complex atom? So when we look at these, we can see, process of elimination, that krypton would be the lowest in order of increasing standard molar entropy. It's a free atom. So this is not going to be wrong. This is going to be wrong. So it's one of these two. The next one would be more complex. And I'm going to say it's chloride, because this has two molecules together over a free atom, but it doesn't have four. This is in total of four. So I'm going to pick A here, and A is correct. So the more complex it is, the greater entropy states it can have. All right, so review. The third law of thermodynamics states that the entropy of a pure crystalline substance at absolute zero is 0. Standard molar entropies for a substance are measured at 298 K, and we can find them at table 18. No, I think I'm on table 19. Sorry, I should have removed this and I should have removed this. But these are in your textbook at the end. There is a list. And sorry, this is also, I didn't catch this. But you see that we've already discussed how to set this up to determine the change in entropy and whether it's